We are now into module 5 and I would like to give some topical studies on the properties of solids, especially with respect to conductivity and magnetism. One of the oxides that we have seen in the earlier module is the perovskite oxides, and among perovskates there are different class of compounds, those which are superconducting, those which are showing interesting magnetic and electrical properties. And today I will give a case study on rare earth manganites, which is a very popular perovskite type of compound. And what is interesting is a combination of both electric and magnetic property coupled together. This makes it a very special series of compounds for spintronic applications. So, today we will be actually dealing with manganites and see what is important in these manganites and how this can functionally become useful for applications. And before I take you through, there are three class of compounds which are useful as far as conductivity is concerned. Electrically they are more conducting, as a result they stand out among the class of oxides, and notably lanthanum strontium cuprate and afterwards high temperature cuprates like yttrium barium copper and mercury based superconductors have taken the limelight, where a phenomenal change in resistance leading to superconductivity is noted, and this was seen in 1986. And the other group of compound which is of interest for today's class is the manganites, which was reported as early as 1950s by Yonker, who has done a phenomenal amount of pioneering studies in these manganites, and who first noticed that manganites which are insulators can also transform into a metal and a ferromagnet. So, what is the property that is of importance for us in the present scenario? Since 1994, many groups of researchers including us have reported a colossal change in magnetoresistance, and which means there is a huge change in resistance on applying magnetic field. So, this will be the topic of our study today. And another class of compounds which was inferred in 2001-2002 is cobaltates, which shows Curie-Weiss metals. So, what is this colossal magnetoresistance? This is a cartoon that clearly tells us that there is change in the resistance or change in resistivity when you apply magnetic field or when you have absence of field. At 0 Tesla, that is absence of magnetic field, this is the insulator to metal transition that you see here. But once you apply a very high field of the order of 6 Tesla, you see that the transition shifts to the right side to higher temperature, and also the resistivity falls down by orders, and this is the term which is used for colossal magnetoresistance, meaning there is a huge loss in resistance when you apply a magnetic field, which has never been observed or reported in any oxides thus far. So, as the temperature is increased through the ferromagnetic Curie temperature, the electrical resistance rises sharply and becomes strongly dependent on the applied magnetic field. Now, this is coined in different ways. It is called magnetoresistivity, or it can be called as giant magnetoresistivity because of the huge loss in resistance, or it can be called as colossal magnetoresistivity. It is popularly known as CMR manganites or CMR oxides, mainly because this term is actually used for another class of compounds which are called metallic multilayers. So, this GMR term is actually attributed to metallic multilayers. The CMR is generally referred to manganites. So, what really brings about such a colossal change in the resistance? It is the substitution of divalent alkaline earth metals in the lanthanum site, which is La3 plus Mn3 plus O3. If you substitute strontium in the La3+ site, then you can see for charge neutrality part of Mn3 goes to Mn4+. As a result, you have mixed valency, which brings about this unique colossal magnetoresistance. So, mixed valent manganese shows unique electronic magnetic properties, which we will be seeing from now on. As an outline of this talk, I want to call this perovskite manganite to have a genie inside the lattice, because something very unusual of this lattice is simple lattice unit cell, but just by mere substitution a big genie comes out of this lattice. So, I call this as the genie inside the lattice, because there are several things that one can learn, one can infer, and also one can use this judiciously to extend it for practical applications. The three factors that really control this unit cell or this manganites I have identified as the X factor, because it is easy for us to remember. X factor, which really brings about a magnetic interaction called double exchange interaction, and there is a R factor which brings about charge ordering or a electronic traffic jam of the itinerant electrons, which suddenly converts a metal into an insulator, and the D factor, which we call it as dimensionality, which will be helpful for us to tune the Curie temperature. So, there are three factors. As we are conversant with the X-ray diffraction, I just coined this as XRD factor just to make sure that we remember it. So, three factors are there which governs this genie inside this lattice, which we call it as X, R and D factor. Now, as I told you in the earlier classes, we have seen the structure of these perovskites. The basic structure that we will be time and again looking at is this MnO6 octahedra, and this is your rare earth that is sitting in the middle, and this is made of a corner shed polyhedra of MnO6 octahedra. So, this is the unit cell, and in this you would see a phenomenal change in the properties. So, what is the genie inside this lattice? Let us ask this question again. La MnO3 is there, which has La in 3 plus, Mn in 3 plus, and this is known to show antiferromagnetic ordering. In other words, they show a Néel temperature at 140 Kelvin, and at antiferromagnetic transition it is also a insulator from then on. So, if you cool this compound, you will see this compound showing a insulating property. But what happens then on is interesting. If you suppose vary the A site by substituting either with calcium, or if you substitute with strontium or with lead, you will see phenomenally something happens to the magnetism and to the conductivity of the solid. What happens from an antiferromagnetic state, it goes to a ferromagnetic state, and from an insulator it goes to a metal. So, two things happen when you try to substitute at the lanthanum site. One is it brings about a magnetic transition, and then it brings about a electronic conducting transition. Now, this Tn now becomes Tc because it is ferromagnetically ordered. As you may see here, I am not changing the La composition or the Mn, I am only changing the alkaline earth, but you could see as a function of the ionic size of in the A site, you can see the Curie temperature is increasing. Therefore, this is merely a chemical pressure effect that transcends in this lattice, and therefore, you can play around with n number of substitution to realize a choice ferromagnetic metal, which will give you a transition that you desire. For example, if you are looking for applying this in practical purpose, then one would resort to using these compounds for practical application which is usable at room temperature. In such a case, one would resort to compounds like strontium doped or lead doped manganites, so that you can play around with the Curie temperature which is close to room temperature. So, it gives a range of properties which are fundamentally and from application point of view it is very important. We look into the next slide and see what is this strange co-occurrence that happens which distinguishes this manganese. This is a plot of normalized resistance versus temperature, and also I am plotting on the other y axis magnetization versus temperature. Now let us take this magnetization which is temperature, which is given in this blue curve. As you decrease the temperature from 300 to lower temperature, you can see a transition where magnetization switches from a very low value to a sudden increase, and then on it shows a practically no change or temperature independent ferromagnetism. So this change is called ferromagnetic to paramagnetic transition. This is your paramagnetic state, this is your ferromagnetic state, and this is the transition which you call as Curie temperature. So Curie temperature is precisely somewhere around 260 or so, and this is for a compound such as La 0.7, Ca 0.3, MnO3, which shows a Curie temperature at 260 to 270 Kelvin. But what is interesting is, if you see the normalized resistance as a function of temperature, you would see that there is a insulating phase, and then at this particular temperature where it matches with Tc, the resistivity curve changes its direction and becomes more metallic, and it is metallic down to low temperatures. So from an insulating state it goes to a metallic state at the same temperature where a ferromagnetic to paramagnetic transition occurs. So two things happen which I call it as co-occurrence. Okay, two things occur at the same time, the ferromagnetic transition and the metal to insulator transition. That makes this group of manganites very special. Now this we can understand from this cartoon, where I have tried to mention what exactly happens for this co-occurrence to effect. Now if you substitute calcium here, as I told you, Mn3 plus, part of it has to go to Mn4 plus, because it has to preserve the charge neutrality in this compound, because charge neutrality comes when A is 3 plus, B is 3 plus and oxygen is 2 minus. So essentially you have 6 plus and 6 minus, making this lattice electrically neutral. So when you have calcium doped here, part of the manganese 3 plus is actually promoted to manganese 4 plus. Now in that case you have the Eg orbital of 3 plus, which has a odd electron Eg1, and you have a Mn4 plus core which has a empty Eg orbital. Now when that happens, there is a tendency for this Eg to go to Eg0 vacant orbital via this oxygen 2p orbital. So the exchange has to happen from here to here and here to here, and this has to happen here to here. In such a situation, what is required of the symmetry is that this odd electron, Eg electron, has to have a same spin as that of the spins of T2g electron, because this T2g 3 electrons are more localized, and with respect to this electrons, this Eg electron has to get ferromagnetically coupled. So this happens when this electron gets promoted to the empty Eg orbital of Mn core, then another thing happens, this Mn3 becomes Mn4 plus becomes Mn3, and this Mn3 now becomes Mn4 plus. As a result, now a back exchange can happen where the Eg1 here can go to Eg0 there, therefore itinerancy is initiated. In other words, the electron becomes itinerant, so you would see the transfer is happening back and forth, which we call it as double exchange. In the next slide we can see this more clearly. this is the cartoon which tells how this exchange happens, and as you notice, this upspin Eg electron has to be ferromagnetically coupled to the 3 T2G electrons of the Mn4 plus core, and this is done by strong Hund's coupling, we call it Hund's coupling, and because of this Hund's coupling you have a ferromagnetic exchange that is initiated, and this was actually proposed by Zener, who said that for the transfer integral to happen, it depends on cos theta ij between these two core spins. So, if these spins are going to be at 180 degree, then there is a collinear ferromagnetism that can be affected. It is called collinear ferromagnetism when this angle theta ij is equal to 180 degree. When it deviates from 180 degree lower than 144 degrees, you will see that this exchange is no more happening. The maximum that this exchange can happen is somewhere around approximately 174. Beyond that, you will get the spins locked up and there will not be any transfer happening between these two core spins. Therefore, this is very important. The transfer of this double exchange integral, transfer integral, has to be comparable such a way that your cos theta ij facilitates such a interaction, and that is crucial for this double exchange to happen, and this was proposed by Zener as early as 1951, and therefore, this is popularly called as Zener double exchange mechanism. Zener double exchange mechanism. Now, we will see that this is not the only condition that governs the metal to insulator transition, and this is not the only thing that is responsible for the paramagnetic to ferromagnetic transition, but there is another cooperative effect which is acting in this manganites, which is crucial for this ferromagnetism and for the magnetic property to coexist. One thing that is popularly inferred is the Jahn-Teller distortion. As we know that this Mn3 plus has degenerate 3d orbitals, which in the crystal field is split into T2G3 and Eg1, and in such a case you actually have a cubic MnO6 octahedra which is undistorted. But what happens when this electron is now transferred to another Mn4 plus site? Now there is a distortion happening between the Eg orbitals. In other words, the Eg orbital is split into further into 3 z square minus r square and x square minus y square, and as a result there is a lowering of symmetry happening during the hopping. So this octahedra further gets distorted when such a hopping takes place. In such a situation, what happens, the electron which is conducting, which is responsible for conduction, is now dragged by this lattice distortion and results in a polaron formation, and because of this polaron, which is much bigger in size, it travels slowly, and as a result the metal slowly becomes an insulator. So if you want to freeze this polaron, what you can do, apply a magnetic field, and on application of magnetic field there is more and more of ferromagnetic ordering initiated. As a result, the polaron formation will decrease. When polaron formation decreases, then again the insulating condition fades out and then the system becomes more and more metallic. So the double exchange or the CMR property in this oxide can be explained by two ways. One is by understanding with respect to Zener double exchange mechanism, and then you can also understand it based on Jahn-Teller distortion. Both are operating in this small unit cell, and therefore we can sort of sum up to say that the Jahn-Teller distortion couples the magnetic and the lattice systems, resulting in electronic lattice and magnetic degrees of freedom intimately twinned. Therefore, this cooperative issues present in the unit cell of manganites makes this a more interesting system to study. So, what in essence happens here is a situation where if I start doping calcium in lanthanum calcium manganite series, you would see as you increase the calcium content across the cartoon here, you would see there is a change in the magnetic and electrical resistivity phenomenally. When you substitute for up to 10%, you see there is a change from a canted antiferromagnetic state to a ferromagnetic insulator state. It is ferromagnetic, but not necessarily it is metallic, and there is some amount of charge ordered state that is there, which I will explain later. And once you go further doping with calcium, from a ferromagnetic state it goes to a ferromagnetic metallic state, and this is the regime of interest for us, because this is the place where lot of application can be harvested. This can be used for variety of applications, because this is the state at which there is huge loss in resistance. And as you would see in this regime, for a nominal composition of 0.33 calcium, the ferromagnetic transition becomes maximum, and after that it starts fading down, but then it is also affected by another big domain, which is either charge ordered or which is antiferromagnetically ordered. So, the system does not necessarily remain in metallic state for a long time. There is a critical composition which falls incidentally at 0.5. Beyond 0.5 still there is some amount of magnetic exchange, but it is all taken in a reverse direction. In other words, from a ferromagnetic it becomes an antiferromagnetic state, and it also shows unusual charge ordered manganite state. So, in a simple system, if you keep changing calcium, you come across a variety of magnetic and electrical transition. Now, to sum up, what is crucial for these manganites? How can I tailor these manganites, or what really happens in these manganites? I would like to sum up to say that despite all the fundamental changes that happens during substitution, what is important or the core of the manganite chemistry is this Mn3 Mn4 plus pair, which is called Zener pair. Now, the Zener pair, if it is disturbed, then the magnetic and conductivity immediately changes. So, that is very important. So, what we are going to see in the next few slides, we are going to sort of disturb this Mn3 Mn4 plus ratio, okay, such a way we will either lose the magnetic property or lose the metallic property, and try to see how we can restore it back. So, this is what I am going to sum it up in the next few slides. What happens if the Zener pair is distorted by substitution of some other metal ions in the manganese site? As I told you, if you substitute in A site, that is lanthanum site, then Mn3 plus goes to Mn4 plus, which is advantageous for us, and therefore you see a ferromagnetic ordering and a metal insulated ordering which is increasing as you generate more and more of Mn4 plus up to a critical concentration of say 33% of manganese 4 plus. Beyond 33% of manganese 4 plus, you do not see any net change or a spectacular change. In other words, sometimes it becomes detrimental. So, this is the optimum at which you can get a maximum Tc and maximum metal to insulator transition. In the next slide, I will show you, suppose I substitute iron or germanium in manganesite, where I am going to keep this A value constant. A is constant, therefore, the changes, anything that happens will be as a result of iron or germanium. What happens here? These are the two magnetization versus temperature plot. These two cartoons are to show they are the resistivity change as a function of temperature. As you see here, when you dope iron starting from the parent compound, you can clearly see that the Tc decreases as a function of iron, and what is the concentration up to the 0.12 iron 0.12, which means just for 12% of iron substituted in manganese, you almost kill the ferromagnetic ordering. Practically it goes very weakly ferromagnetic, and the same situation is there when you look at the resistivity versus temperature function. As you increase the iron concentration to 12%, it completely transforms into a insulator. Same situation for germanium. As you substitute, you see the Tc decreasing, and as you substitute for germanium, you see the resistance going almost to a insulating stage. So, even in this case you can see that it happens at 10% of germanium. So, you have either 12% of iron or 10% of germanium totally killing the ferromagnetism and the metal insulated transition. In the next graph I will show you for other transition metals. Suppose it is only manganese, then manganese 3 plus manganese 4 plus concentration is like this, and therefore you can see a double exchange mechanism very strong in manganese. But if you are going to substitute chromium in the site of manganese, you can see that the metal insulator transition is happening up to 20%, although ferromagnetic transition is still there up to 50%. This is a very strange thing, that you can see ferromagnetism equally strong up to 50% of chromium, whereas for the metal insulator transition it deviates. But the real signature for a double exchange mediated ferromagnetism is that both the Tc and Tp or the metal insulated transition has to coexist like this. Both has to be like this if it is truly mediated by a double exchange model, but this is not happening in chromium. And if you see iron, as I showed you in the previous slide, both are killed at around 12%. Another interesting substitution comes from ruthenium. If you substitute for ruthenium, metal insulator transition is taken up to 40%, and you also see a strong ferromagnetism up to 50% of ruthenium. Therefore, something very interestingly happens in the case of ruthenium substitution, but by and large when you try to disturb the Zener pair, then the metal insulated transition is decoupled from the ferromagnetic to paramagnetic transition, that is Tc. So, I am going to show you some examples of ruthenium substituted ones to understand what all chemistry that we can understand from this manganites if you substitute ruthenium, and in the end I will also try to make some conclusions what is so special about ruthenium and manganese, especially in manganites. I am taking this case of ruthenium because we can understand many more things about this gene in the manganite lattice, and also we bring special correlations between two dissimilar metals. Now, the first point that I want to cover is the X factor in manganites. Very easy to register because X is something that you would like to always mention. So, X factor in manganites, this has both to do with A site cation, you can substitute 1 minus X, or B site cation you can substitute 1 minus X. I have shown you lot of examples of A site substitution. So, I will be by and large I will be focusing on B site substitution, mainly substituting ruthenium 4 plus in the manganese site, in the manganese Mn3 plus Mn4 plus site. So, what would happen if you substitute in equal proportions? I take a case study of strontium ruthenate and strontium manganate because this is more of a reverse doping effect. This is a ferromagnetic metal which is known, and one of the very popular ferromagnetic metal known in the ruthenate series or among ruthenium oxides. And on the contrary, if you take SrMnO3, it does not show ferromagnetic metallic state, it rather shows a ferromagnetic as antiferromagnetic insulator state. Now I am going to substitute manganese in this ruthenate. Ruthenium here is already in 4 plus, now I am going to put manganese here. I can do the other way also, take SrMnO3 and I can start putting ruthenium 4 plus here, both are possible, but I am going to start with the ferromagnetic metal to see how long I can sustain ferromagnetism and how long I can maintain this metallicity. So that is another way of seeing what happens to the Zener pairs and when the Zener pair becomes operative. So this is a magnetization versus temperature curve for SrRuMnO3, where we systematically keep substituting manganese down the series, and if you plot magnetization versus temperature, you can see there is a strong ferromagnetic loop that is coming, which is characteristic of these ruthenates, and as a function of this manganese substitution, the ferromagnetism keeps going down. Nevertheless, even at 70% of manganese, you still see a very strong or a clear ferromagnetic exchange happening. So why it has to happen? Because the N member, that is SrMnO3, is an antiferromagnetic insulator but something special should be happening as you substitute. For example, let us take the case of x is equal to 0.5 in SR Ru 0.5 Mn 0.5, you will see that both are in equal proportion. In other words, for every ruthenium you see a alternate ion should be a manganese ion. So in that case we can see what is really happening compared to SrRuO3. Okay. The best way to understand that is do the magnetoresistance curve. This is the magnetoresistance plot. Magnetoresistance plot as a function of magnetic field. So when you swipe the magnetic field in both directions, you will see a enormous loss in the resistance. But what is surprising here is, if you take the x is equal to 0, that is SrRuO3 case where there is no manganese, you can see that the MR ratio, percentage MR ratio at the Curie temperature Tc is only up to 10% approximately, and at 4.2 K it is still lower. Whereas in the case of SR 0.5 Mn 0.5 O3, you see there is a almost 3 times the magnetoresistance compared to the parent compound. So there should be something unusual happening when you substitute manganese in the place of ruthenium compared to the parent oxide strontium ruthenate. That we will see what exactly happens, and let me take you through another example also and show you. Suppose if I substitute ruthenium in manganesite, then keeping lead concentration constant, as a function of ruthenium concentration you still see a very strong ferromagnetic loop. In other words, for even up to 40%, I am seeing almost for every ruthenium there is a nearest neighbor manganese in such a unit cell, you would see a strong ferromagnetic transition happening. So what is that which makes it important? This is also pronounced in the resistivity as a function of temperature plot, where you can see the parent compound is showing a clear metallic transition, whereas 10%, 20%, 30% and 40% of ruthenium still shows a clear metal insulated transition corresponding to the magnetic transition which we saw in this case. So if you take this metal ferromagnetic transitions and if you compare in the next curve with the resistivity plot, you still see a clear correlation happening. So something is very unusual of that. We can also try to verify that by keeping ruthenium 0.2 constant in all these cases, and we can try to vary the lead concentration 0.2, in this case 0.3, in this case 0.4, you can clearly see there is a change in the metal insulated transition, but nevertheless they are still ferromagnetic and they are showing a metal insulated transition. And if you also look at the fall of resistance, say for 0.2 and 0.3, 0.2 and 0.3, there is a huge fall in the resistance for both these compositions. So what is happening is there is unusual correlation that is happening between manganese and ruthenium, which we should take note, and we can try to see what exactly is responsible. So we need to make some correlation now to see why such a spectacular systematic change is happening whenever ruthenium is substituted, especially when we try to alter the Mn3 Mn4 plus concentration. In the next slide I will take you through the other factor called R factor in manganese. So far we have seen the X factor, where either you substitute in the A site, which improves the ferromagnetic transition, or in the B site, which tries to destroy the ferromagnetic alignment. So in case of R factor, we will try to see what is the influence. R factor is nothing but the average size of A site cation, that is what I call it as R factor, the average size, ionic size of A site cation. Suppose I take calcium, or I take strontium, or I take barium in the place of lanthanum, then the average size of this or this or this will keep changing, because you are going from a smaller cation to a bigger cation. As I change this, what will happen to the ferromagnetism and metal insulated transition? As you know, in the previous slides, in the other modules, I have discussed with you about the perovskite structure, and what is important for the perovskite structure is the tolerance factor, which was proposed by Goldsmith, and this tolerance factor is very critical, and if you have the optimum average RA size, then you would get a perfect octahedra. Okay, this is a cubic unit perovskite cell, but once you start substituting bigger ions in lanthanum site or smaller ions, they can get distorted, and therefore there is a critical tolerance limit to which we are bound, and that is actually mentioned by this tolerance factor, which has to be not less than 0.89 and it should not be more than 1.02. In that case, anyway, beyond these extremes, this perfect MnO6 octahedra gets distorted, and this is what we have seen in the earlier stage. So whenever we are increasing the size, average size, there is a positive influence where ferromagnetic Tc is increased from antiferromagnetic state, and if you go further, then this ferromagnetic state again transforms back to antiferromagnetic state. Therefore this average A site value is critical, which we will see in the next few slides. So what is the average RA site that is needed? The critical one is 1.17 angstrom. If it is less than 1.17 angstrom, then the compound immediately becomes a paramagnetic insulator, which we have already seen in this phase diagram earlier, and this is also seen in other stoichiometries or other compositions. LaSr MnO3, you can see up to 0.5 you can have Tc, and then it slowly transforms to charge ordered state. Neodymium strontium manganate, here I am changing the lanthanum by neodymium, again you would see after a ferromagnetic state around 0.5 you see a charge ordered insulating phase coming. Similarly the case for praseodymium, it is more complex than other series because praseodymium itself has a variable valency. As a result, the MIT and ferromagnetic transition gets distorted. So, differences due to changes in cationic radii Ra, this brings about a charge ordering because there is bending of MnO Mn bonds. So, when MnO Mn bonds are distorted or it deviates from 174 degrees as I told you earlier, then you would actually go into a charge ordered state, okay, which means there is a competing interaction between the itinerant electrons which causes a double exchange mediated ferromagnetism and a super exchange competing magnetic ordering, which will actually bring about a charge ordered state. The super exchange mediated ordering leads necessarily to antiferromagnetic state. The double exchange mediated ordering leads to ferromagnetic state, and because you are distorting this Mn O Mn bond, you are actually going into a situation where it is charge ordered. In other words, there is a sudden twist in the Mn3 plus and Mn4 plus orbitals and they become orthogonal. As a result, there is no collinear magnetism and there is no exchange transport of electrons. As a result, the system suddenly transforms to a insulating stage. Okay. So, it is a extremely sensitive composition to small changes which brings about such a drastic change. Now, this is another figure that I have taken from paper of Ravo from France. This is appeared in Chemistry of Materials volume 10, and this curve also shows a plot of Tc, that is Curie temperature, as a function of Ra, because if you keep on varying the Ra value from 1.17, as you know here it has gone into a paramagnetic insulating stage, whereas if you start increasing this way, then you again transform to a ferromagnetic metallic stage. So, from a paramagnetic metal to a ferromagnetic metal, the critical tie line seems to be something like this, where you have a critical boundary which separates both these behaviors. So, Ra, average Ra is very important. We can also make a function of Tc as a function of Ra, where you can actually try to choose different sort of compounds. Praseodymium 0.7, calcium 0.30, praseodymium 0.7, lanthanum you can substitute little bit for praseodymium and you can keep the calcium constant, and calcium is kept constant, then you can vary praseodymium kept constant, you can vary calcium for strontium. You can see a variety of trend that is available. Okay. For example, take the case of C, where a bigger ion is brought in which has 3 plus, immediately you see the transition is increasing on the higher side, whereas if you take B, which is the lowest, because you are bringing in more and more of a divalent ion, you are seeing the the average A size, although here, but it is essentially decreasing the Curie temperature. So, it is not just necessary that you play around in this domain where the values are low, because you are essentially trying to disturb the Mn3 plus Mn4 plus ratio there. Okay. So, what is so critical here in this R factor is that magic value of 1.17. So, it is possible when you are trying to make new compositions always to have two things in mind. One is you should always have Mn4 plus ratio which should be approximately 30%, and you should have your average A size value which should be always above 1.17 angstrom. So, this you do not even need to do the experiment, you can actually calculate if you know the ionic size and ionic and the valency of your substituting metal, you can principally calculate this, and also the tolerance factor you can calculate, which should be approximately 0.95 or so to keep up with the perovskite phase. So, this is more like a mantra, more like a thumb rule for magnets, that you need to comply with all three to look for a ferromagnetic metal. This is another very interesting case where you see praseodymium is in a charge ordered state, because you have substituted up to 0.5. Therefore, this is a charge ordered situation where this is your ferromagnetic transition and this is your antiferromagnetic transition. So, from a paramagnetic it goes to a ferromagnetic transition and then it comes to a antiferromagnetic transition. This is clearly seen because if you do the resistivity versus temperature plot, up to this place it is more or less a weakly metallic state and then immediately it goes to a insulating state. At the nil temperature there is also a insulating phase. Now, what can we do about it? If you try to apply magnetic field, you can see immediately you can melt down this insulating phase to a metallic phase if you are going to apply 7 Tesla, a very high magnetic field. In other words, you can melt the charge ordering. You can melt the charge ordering mainly using magnetic field. Okay. There are other reports where you can melt this charge ordering by applying very high pressure. It is called pressure effect, but from chemistry point of view this pressure effect can be brought in simply by altering the cubic lattice. In other words, the pressure can be exerted within the unit cell by substituting a smaller or a bigger ion, which we can see. So, this is another compound, neodymium strontium manganate, which is a very popular example for a charge ordered magnet where it goes from a ferromagnetic state suddenly falls down, and the same is true for the resistivity versus temperature plot. Exactly at the nil temperature you also see the charge ordered state that is coming, which makes it. But the classic example comes from Professor Rao's group in 1999. They did this work where they have taken the neodymium strontium manganese and they have substituted for little amount of ruthenium. What is the amount of ruthenium that is added? It is 1%, 3%, 5% and they have gone up to 10%. What is interesting here is the moment you start putting just 1% of ruthenium in this charge ordered manganate, immediately this charge ordering is removed and the system becomes a ferromagnetic metal. And as you substitute more and more of ruthenium, the system is becoming more ferromagnetic, and therefore, from a charge ordered or a antiferromagnetic state you can make it a ferromagnet by simply substituting with ruthenium. Okay. Same is true when you look at the resistivity versus temperature plot, where you can clearly see that from a charge ordered situation where it is insulating, you can melt this by substituting with ruthenium. Okay. So, from a insulating phase you can go to a metallic phase by substituting for ruthenium in the place of manganese, or you can drive the antiferromagnet to a ferromagnet by ruthenium substitution. Why this happens we will look at it shortly from now, but before that let me touch on the other aspect, that is dimensionality, which I call it as D factor in manganese. Take the example of a layered perovskite. This is a 2-dimensional manganate where the MnO6 octahedra is here, there is another MnO6 octahedra here in a polyhedral fashion. You also have a MnO6 octahedra here, but it is separated by lanthanum ions. Okay. So, the ferromagnetism present in this polyhedras is confined only in 2 dimension and it is not coupled in the 3 dimension because it is separated by the lanthanum oxides. Okay. In such case you would see for a parent compound the ferromagnetic transition is somewhere here, whereas if you start substituting ruthenium here in manganesite, you would see that there is a increase in the ferromagnetic transition up to 20%, and then the ferromagnetic transition drops down. Okay. Now, if you look at the metal to insulator transition, that is again interesting. You would see this as the metal insulator transition for your parent compound, whereas if you substitute for ruthenium, the metal insulator transition shifts to the right side for when you have calcium, and it is much more interesting if you are going to substitute ruthenium keeping strontium instead of calcium. You would see the ferromagnetic transition is now on the increase from 110 to nearly 170 Kelvin. Increase of about 60 Kelvin you can bring about if you substitute ruthenium for with a bigger size cation. The same is true in the metal insulated transition, where you see a clear increase in your metal insulated transition going hand in hand with your magnetic ordering. So, what really happens in this case, why ruthenium has to increase the ferromagnetic transition? As I told you, manganese 3 plus, manganese 4 plus is very intricate. When you substitute, it should actually kill ferromagnetism and metallicity, whereas in this case it is actually on the reverse gear. It is increasing the metal insulated transition and it is increasing the ferromagnetic transition. Therefore, there should be something unusually happening with ruthenium, and especially in this layered perovskates, and that is what we will see in the next few slides. You can see here the spin orientation of the manganese core spins are actually confined in the AB plane, whereas when you substitute ruthenium from the neutron diffraction studies, it says it clearly tells us that there is a rotation of the spins along the C direction. It is no more confined in the AB plane, it is now coupled in the C axis. Now, when it is coupled in the C axis, this can promote or enhance your ferromagnetic ordering and your metal insulated transition. It is not a guess, we can see that from the neutron diffraction case. This is the neutron diffraction profile at 300 K, but let me take you to the low temperature neutron diffraction profile, where you clearly see that in the case of the ruthenium substituted compound, this 004 neutron reflection or magnetic reflection is absent, whereas this 110 is actually increasing. What is true about that? 004 is absent, which is actually representing the AB plane orientation. Spins aligned in AB plane will have a characteristic 004 reflection. Therefore, if it is turning more magnetic in the layered perovskate, this intensity should keep increasing. On the other hand, what happens in ruthenium is this is nearly absent and you have this 110 which is present, which means there is a interaction along the C axis. Nevertheless, we confirm this spin state. So, when you substitute for ruthenium in the manganese site, you are actually rotating the spins ferromagnetic alignment along the C axis. As a result, you are enhancing the properties. So, what is crucial for these interesting observations in ruthenium substituted magnets? The next question we can ask, why is this cooperative effect more pronounced in ruthenium substituted magnets? Okay, these two questions we will try to understand from the spectra. This is a X-axis spectra of ruthenium L23H, which actually shows there is a systematic change in the ruthenium H when compared to your SrRuO3, because SrRuO3 actually is supposed to be 4 plus, whereas in this case you would see the peak maxima is shifting to the right side. Another example, this makes it more apparent. This is SrRuO3, which is a standard, which shows your RuL23H here, and in this case you have where we have substituted for SrRuO3, it is lying between 4 plus and 5 plus state. Therefore, your ruthenium is in 5 plus 4.5 state. It is neither 4 nor 5. So, we can sort of sum up with a new double exchange model where we say that Mn3 plus Eg electron now has both ruthenium 4 plus and ruthenium 5 plus, and as a result this Eg electron either can go here or this Eg electron can go to this empty orbital. Therefore, you have a 2 double exchange pathway where you can drive this compound metallic and ferromagnetic because you are providing a similar state. In other words, this Mn4 plus is isoelectronic and having iso-orbitals like ruthenium, which makes this a more important compound to study. Not only that, ruthenium 4 plus and 5 plus redox is comparable to that of Mn3 plus 4 plus. As a result, you will have a redox mechanism that is happening. So, whenever you substitute ruthenium 4 plus into this Mn3 Mn4 plus pair, you will see part of your ruthenium 4 is promoted to ruthenium 5. As a result, you are clearly providing a 2 exchange pathway in this manganites. So, to conclude, let me put it that we have seen XRD effect in this manganites, which I call it as the genie in this manganites, and we have taken example to see how this manganese 3 plus 4 plus core, when it is disturbed, it can still bring about a very rich chemistry, especially with substituting ruthenium, and we have seen how the dimensionality works, especially when you substitute ruthenium, where you twist the spins along the C axis. So, in essence, manganites are a very interesting set of compounds that provides you rich chemistry and physics, and there are a lot more examples that we can study along the XRD effect in manganites. With this I conclude this talk. We will look at the other aspects later.